We have dealt with a fault propagation fold. Now we are going to see a fault bend fold and the application of the theoretical fold models in it. The excess area diagram and the fault bend fold will together be seen. In this diagram, here is the upper flat, also we can call it upper detachment, and here is the lower flat, or we can call it as a lower detachment. Connecting them is the slanting ramp. We are dealing with upper flat or upper detachment, then a ramp, and then a lower flat or the lower detachment. This is the geometry of the footwall block, and above it consider this layer to start with. Apply a push from right towards left. If this happens, then consider a rigid flat that does not move, that does not deform, so that this particular line moves from here to there. And then what happens to the internal deformation we are going to see in this diagram. Within the footwall block, consider a layer here, and before deformation it was like this. As you have compressed, this line has moved to say this place, and as a result this particular line within the hanging wall block got deformed and has attained this geometry. It has climbed over the upper flat, and this is the geometry produced. In this case, the excess area is S1 shown by the dotted region. Note that this is not a trapezoid. See the geometry clearly. This is not a quadrilateral, in fact. 1, 2, 3, 4, 5, 6, it is a hexagon of irregular geometry. What I have explained in terms of excess area for layer 1, this one we can call as layer 1. From there we can find out the depth of the lower flat or the lower detachment as small h1 by the method. Now consider this particular layer, call it the layer 2. What will happen to layer 2 after deformation? This has come like this. Okay. If I draw this line here and draw a line there, this forms a trapezoid and the excess area is S2, but this is not the entire story. As this push happened, some material also went outside the area of consideration, and we can call it as the delta S2 area. So the excess area for layer 2 is not just S2 but S2 plus delta S2. But for layer 1, excess area was S1, there was no delta S1 term involved. Here we mean delta Si is the area that goes out of the section. In other words, when we are considering a layer above the upper flat, where is the upper flat? This is the upper flat, and this is layer above upper flat. We need to bring delta Si term, which in this case is delta S2 term. Whereas for a layer 1 which is below the upper flat, no such delta Si term is there, or delta S1 in this case is equal to 0. So that explains these two sentences and also these sentences. Now we will add a few parameters in our diagram. Consider HU is the elevation of the upper flat with respect to the lower detachment. This is the lower detachment or the lower flat, and this is the upper detachment or the upper flat. The distance between them is considered as HU. This also can be called as the ramp height. So in this diagram, the ramp height is given by HU, that has been done here. Small d is the displacement on the upper flat. For layer 2, this much is the displacement, so this is small d, this is the displacement on the upper flat. So for layer 1, we can say that S is equal to dH. This is our layer 1, and after deformation it has gone like this. There the formula S equal to dH will work. From where we got it? We got from here, same philosophy, S equal to dH, but it does not work for the layer 2, which after deformation looks like this, because there is a delta S2 term. So here for layer 2 it is dH2 is equal to S2, the excess area here, plus delta S2. Now delta S2 can also be expressed in another way. Consider this height to be H2 and this height to be H1. Therefore, delta S2 will be given by small d, rectangle's area we are finding, small d multiplied by H2 minus Hu, because this distance is H2 and this distance is Hu. So, what remains here is equal to H2 minus Hu, that is being made. So, we have got these two equations, and these two equations I am going to write in the next page as it is, and along with this diagram we are going to proceed. So, these are these two equations, call them equation 1 and 2. We can eliminate delta S2 from the above two equations. This means what? This expression will be put here. Once I do that, I can find out expression for capital S2. Just recollect what is capital S2. This is a part of excess area over here, that is equal to, from these two equations, d minus d, capital D minus small d multiplied by H2 plus d multiplied by small Hu. So, for all H values more than Hu, that means for all H values such as H2 more than Hu, which means lines above the upper flat, for all levels above the upper flat, this equation holds true. What I did, from S2 I wrote S, d minus d is written as it is multiplied by H2. Here I just wrote a general form multiplied by H, and d multiplied by Hu, we write here d multiplied by Hu. This line can be plotted on the excess area graph. This is the excess area plotted along y axis S, and H is plotted along this axis. H has various level wise terms such as H2 and H1 here, and this is the line S is equal to d minus d multiplied by H plus dHu. This is our equation 3. This is equation 3. Note that if you put small h equal to 0 dHu, which means that this line intersects the S axis, which is the y axis, at the coordinate 0 from here, comma, and then dHu. This is the plot dHu. That means if I extend this line here, I get the dHu coordinate along the S axis. So, for all levels above the upper flat, the line is here, and here is the term dHu, and for all levels below this upper flat, such as layer 1, we can draw our conventional line. We can draw this line, which is S equal to dH. From where we got S equal to dH? We got it from here. These two lines, S equal to dH and S equal to d minus d multiplied by H plus dHu, if I solve these two equations, I find the coordinate, the x coordinate is Hu, and that is the upper detachment. Let us prove it, why it is so. First, let us write this equation, S equal to d minus d H plus dHu, and there in S I am putting capital DH. So, DH is equal to DH minus DH plus dHu. DH cancels out. From here I can write DH is equal to dHu, and then D cancels out. What remains is H is equal to Hu, and that is plotted here. Hu is the upper detachment height from the lower detachment, as it was defined here, or as it was defined here. Along the H axis, along the X axis here, for H more than Hu means is the level above the upper detachment. This is my upper detachment. Any line above that will be considered as H more than Hu. H is equal to Hu is the same level as the upper detachment. This upper detachment itself is the level for H is equal to Hu, and H less than Hu is for the level below the upper detachment. So, if I can draw S equal to dH line and S equal to d minus dH plus dHu line, and if I find their intersection, I need to find out the x ordinate of this intersection, and that gives the desired Hu that we were trying to find out, the depth of the lower detachment. Let us understand this statement: excess area data collected from above an upper flat. That means this is my upper flat. For any layer above the upper flat, such as say this particular layer I have worked out, and I try to find out the excess area, and we draw this line. If I extend this line, it will intersect the h axis somewhere, but that will not give us the HU value, because HU value is not there, HU value is here. If I draw this graph here, so level 1 is drawn, d s equal to dh line passing through the origin, and a level has been drawn which is above the upper detachment. Now, if I extend this line and let it intersect the h axis, this particular point is not HU, rather where is HU? As I have explained, it is over here. Find out the intersection point, go vertically down, this point marks the HU along the h axis. This is the meaning of this statement. So, how do I find out the HU? We need to draw the curve for at least one line, at least one level which is above the upper detachment, such as level 2, and at least one line below the upper detachment, such as level 1, and after plotting them, find out the intersection and go vertically down, find out the HU. That is the meaning of this statement here. What we have learnt just now can be applied on a fault bend fold with multi-layer. Consider there are 6 layers, 1, 2, 3, 4, 5 and 6, and here is the lower flat or the lower detachment, this is the upper flat or the upper detachment, and this is the ramp. Below the upper flat UF lies the original lines 1, 2, 3 and 4. These 4 lines lies below the upper flat, and the lines 5 and 6 lies above the upper flat. So, if we do the area balance and find out the depth of the lower flat LF or the lower detachment LD for line 1, 2, 3, 4, since they lie below the upper flat, it will be a straight line which is drawn here. Points 1, 2, 3 and 4 are plotted in the depth versus excess area S diagram. They fall in a straight line, but note that this straight line is not passing through the origin 0, 0. Now, since lines 5 and 6 lie above the upper flat, once they are plotted, they actually plot in another distinct straight line. So, this straight line and that straight line are distinctly different. Point 1, 2, 3, 4, these represent lines below the upper flat, and points 5 and 6 plotted actually indicate the lines above the upper flat. Now, their intersection can be obtained here, and if I go vertically down, I will find the HU, and from there the lower flat or the lower detachment can be drawn. This lower line segment, this has been called as a lower line segment, has an equation S is equal to 5.52 H1 minus 0.30. And if I compare with the equation S equal to dH1, and it is going to be a partial comparison, we can say that D is equal to 5.52 centimeter, which is the slope of the line. Just to recollect, what is D? D is the total displacement of the pin line. Here in this diagram, we have not shown the pin line, but if you draw, imagine, visualize, and then we have to work out that capital D, the movement has been in this direction 5.52 centimeter. Considering that this is a rigid side, this is the pin line and this one is the loose line final. The loose line initial was somewhere here. Now, the upper line segment has an equation for this line, S is equal to 1.64 H5 plus 8.45. And if I compare this with the standard equation, S is equal to D minus D multiplied by H1 plus DHU, by comparison I can say D minus D is equal to 1.64 centimeter from this diagram, and that is stated here, D minus D equal to 1.64 centimeter. Now, from equation 5 and equation 6, we can find out small d is equal to 3.88 centimeter. What is small d? We have not drawn small d, capital D, etc., but you can recollect this diagram. small d is the displacement over there. So, in this particular case small d is equal to 3.88 centimeter. This is the displacement on the upper detachment. This is the upper detachment on which that much of displacement has happened. Now, we have to understand this statement. The computed depth of lower detachment is 0.05 centimeter above the reference level. What does it mean? For that, let us go back to this particular diagram. Note that the lower segment of the line here passes through the origin 0, 0, and that has been identified as the lower detachment, this particular point. And in this case, here is the point. Origin 0, 0 is the reference level, and this particular distance is 0.05 centimeter, and that is the computed depth of lower detachment. This intersection represents the lower detachment's depth, that is 0.05 centimeter above the reference level. Why above the reference level? Because from reference level towards the right hand side, if we move, I get that particular point of intersection between the lower segment of the line and the x axis or the h axis. So, the depth of lower detachment is obtained. Now, we want to find out the location of the upper flat or the HU distance. What is HU here? Draw this line, and this is your HU distance. How to obtain that? We will use equation A and equation B. By comparing these two equations, we know dHu is equal to 8.45 centimeter, that is stated here, and we have already got d is equal to 3.88 centimeter as explained. So, from there, by putting d equal to 3.88 in this equation, we know the HU is 2.2 centimeter. So, in this way, the fault bent fold can be restored using the excess area diagram. Let us try to understand the meaning of the statement. The lower line must always pass through the 0 excess area. The 0 excess area is characterized by this point. This is the depth of the, this marks the depth of the lower detachment or the lower flat, and if we consider a marker along that lower detachment, then that marker does not fold, and therefore 0 excess area is produced. But if the lower line does not pass through the 0 excess area, we may see a few cases. This might be due to some mistake in interpretation of the structures, that this interpreted structure itself is problematic, or it is not a case of ideal fault bent fold. Having said so much, let us take a real cross section where such a technique of area balance and the excess area graph has been applied. This can be the kind of cross section provided by a field geologist and on which the area balance method can be applied. Similarly, this is another example of a structural cross section, and some particular portion of the cross section can be zoomed as has been done here, and the method of area balance can be applied. In case you are trying for the depth versus excess area and your plots are too much scattered, such as this can indicate that, and in the beginning the structure has been wrongly interpreted or the units have not been correlated. That means, suppose starting from such a structure, or suppose starting from such a given real structure, or this particular structure given by the field geologist or by the seismic interpreter, we are getting a scatter of points that indicates that the interpretation has gone wrong. What we expect is a lower segment of line and an upper segment of line, or the graph can go like this, a lower segment of line and an upper segment of line. So, these are correct, and this creates trouble. One needs to go back to the interpretation. So, the excess area graph has also another application of knowing whether the structures have been correctly interpreted. I have followed a single research paper by Eppard and Grossong 1993 to make this video. Consider through field work or through seismic image interpretation, we have obtained two levels, level 1 and level 2, for which folded nature is revealed. From some geophysical studies, we have an idea that at depth lies the detachment, and we want to find out the depth of the detachment applying both folded layer 2 information and also the information of folded layer 1. To do that, let us consider a pin line here. If I take little bit here or there, things will not change, the end result does not change. This is the pin line which is fixed in its position. Let us find out the excess area S1. This is the S1. How much is the area? It is equal to half multiplied by 4.7 multiplied by 0.9 centimeter square. Let us find out the S2 area now. The S2 area is given by half multiplied by 4.5 multiplied by 1.6 centimeter square. Here I have drawn the loose line. Let us change for our convenience the pin line fixed from here to there. It will make our calculation fast. For S2 or the level 2 fold, the AB length plus BC length equals to 2.6 centimeter plus 3 centimeter is equal to 5.6 centimeter. I have to draw a line from A to 5.6 centimeter length along this line, and I reach this particular point. Let us do for S1 the length A1 B1 and the length B1 C1 we are going to add up. 2 centimeter plus 2.7 centimeter, which is equal to 4.7 centimeter. I have to draw a line 4.7 centimeter straight away from here, and I reach this point. S1 area is given by the S2 area is 3.6 centimeter square, the S1 area is 2.1 centimeter square. Now, the S1 area divided by the C1 D1 distance is given by 2.1 divided by C1 D1 distance. 0.25 is equal to 8.4 centimeter, and the S2 area divided by the CD distance is given by 3.6 divided by 1 centimeter, which is equal to 3.6 centimeter.